Merry Christmas! Today I'll teach you some advanced pixel manipulation using vanilla JavaScript and HTML Canvas. We'll make an effect that uses the webcam to show you reflected on this Christmas decoration in real time. To make it appear round like this, we'll need to use some trigonometry and linear algebra. So if you're struggling with these, I recommend you watch my videos on those two topics first. They're worth it, I promise. Now, some of you asked me to talk about time complexity and code optimization someday, and I decided to do it in this video. Normally, I'd say don't be scared, but for that part, you need to be at least a level 7 coder to keep up. Good news is you can skip that part and the effect will still work, just a bit lagging. So don't worry about it, and let's start coding.
Gonna code, debug, and have fun. Coding with Radu, coding with Radu. Gonna prototype and design. Coding with Radu, coding with Radu. Let's code now.
Let's begin with basic HTML. And I can't believe that after so many years of doing this, I just now find out that this is not the opening tag, and I still need to write it here like so. Found out that recently from one of my subscribers. So let's write the head section, and then the title will be a Christmas globe. And close the title. And let's include the CSS here as well. We won't have that much of it, but it's important in this project. Style sheet, and it's going to be called style CSS, like this. Let me close the head, and in the body, I'm going to define two things. First, the video. I'm going to put whatever comes from the camera on a video element so that we can debug. And canvas element, which we will use for doing the image processing and the actual effect. Let me close this one and close the body and the HTML tag. I'm going to save the file and refresh the page. And there's an error here because I didn't define the CSS file yet, but there are some elements here on the screen already. This video and the canvas, they are just invisible at the moment. So I'm going to define this CSS file. I will go here and say style CSS. And let's also add some style for these. So the video, I'm going to give it a background color of dark red. And to differentiate, the canvas is going to have a background color of dark blue. Let's save this and refresh. And here they are, the video element and the canvas element. I don't like these margins almost ever, so I'm going to remove these in the body. I'm going to set here the margin to 0 and save the file, refresh the page, and the margin is gone. So next I'm going to go back to index.html, and I'm going to go at the end of the body here, and I will type a little bit of JavaScript. Eventually we're going to do this in separate files, but this starting part I'm going to do right here. It's just accessing the camera. So let me write here this script tag. And remember to close it. And inside here, I'm going to go all the way to the left so I have enough space. And I'm going to type navigator media devices get user media. And I specify here that I want the video. I'm not going to use the audio in this tutorial. So this will return a promise, and I can handle that by typing then. And here I'm going to pass a callback function with a parameter, which is the stream. So this callback function will get a stream as a parameter, and here I can do something with it. Like I could pass it to my video as the source object and tell the video to play. Now let's close this, and I will also add a catch here. So this promise might not be successful if somebody, for example, doesn't give permission to use the camera when asked by the browser, or maybe if the device doesn't have a camera or things like that. So in case of an error, I'm just going to pass a callback function here that alerts that error. Maybe a better message could be tailored for this, but I'm not going to bother with it. So let me save this and then refresh. Allow, it's asking me to allow, but this screen recorder doesn't show this for some reason. So I'm pressing now this allow button, and I'm in two places right now. Okay, weird. So let me zoom out a bit because this video actually goes off screen quite a bit. And the canvas is still at the bottom, but now the my video element here is really taking up a lot of space. And I'm gonna work zoomed out like this from now. Now here where we play the video, it actually takes a little bit of time for that to happen. And we can detect that with an onloaded data event listener. So I'm going to write here my video onloaded data, and here we are safe to begin our effect. So let me just call begin effect, and this is going to be a function that we are going to implement ourselves. I'm going to set the width and height of this canvas to be the same size of the video because now you can see it there quite small. I want it to be essentially a place for the video to play and for us to do the image processing later on. So let's set the width of the canvas equal to my video width, and the height of the canvas equal to my video height, like this. And to check if the canvas functions properly, we can get here the context by saying my canvas get context 2D and draw an image on this context, specifying the first parameter, my video. So it actually works giving the video, it's going to put first image that is available from that video will be put on the canvas for testing. And we say that we draw this image starting at 0, 0, so the top left corner, and then the canvas width, canvas height, or how much we want this image to stretch. And that's it. Let me close this curly brace. I almost forgot. Save the file and refresh the page. Allow. Okay, so what do we have here? I have to zoom out even more. We have the canvas there. Let me make this console a bit smaller. So here what we have is essentially the first frame of the video after it loaded. That's why it's static there, but it seems to work. So now the canvas is showing an image from the video. And this is the point where we start to work in a separate file because this is like an initialization, and now the actual effect is going to begin. So let me actually remove this code. It was only for testing. And I'm going to put here new effect on my canvas from my video. So output input. And this is going to be a new class that I'm going to define next in its own file. And I'm going to import this file. So let's say here source is equal to effect JS. This is where we'll implement most of the effect. And I'm going to close the script tag. And next, let's create this file. So I'm going here and I type effect.js like this. And inside, I will write the effect class. And for now, this is going to be quite basic. I just want to get the same functionality as before, but maybe animate this bottom part a bit. So let's implement the effect class. And in the constructor, I'm passing here the canvas and the video. So let's store these as attributes of the effect object, like this. And for convenience, I'm also going to set here the context as well. So I don't have to call this get context all the time. This can be also quite slow if done multiple times. So let me also begin the animation loop. I'm going to implement a private method here called animate. So here is where I call hashtag, which means a private method, animate. So this animate method is going to do a similar thing as before. I'm just going to first destructure here CTX, canvas, and the video from this, so I don't need to repeat typing this everywhere. And let's use the context to draw the image from the video at 0, 0, and then the canvas width, canvas height. So pretty much the same code as before, but written a little bit differently. And let me close this animate, save the file, refresh the page. Okay, so the bottom image is different now, but still just one image. Let's make it change in real time. To do that, I'm going to go up here and type request animation frame, and then pass this animate function here. But this as such is not going to work. I'll show you. I'm going to refresh this, and it's not animating. It's actually giving us an error here. It says that CTX of this is undefined. So something weird is happening here, and I'm going to show you by debugging. I'm going to write here log of this. And now when I refresh and allow, it's going to print this. So essentially the effect object itself once, but then we get another print here for undefined. And this happens because when we pass this animate function to request animation frame, it forgets what this is. It's just how JavaScript works. So the problem is that after this request animation frame starts calling animate again and again, animate no longer knows what this is and what the context is and so on. So the way to fix that is to actually pass here this through the bind method. And we are essentially telling animate that this is this. Sounds funny, but yeah, so in this way, it doesn't forget what this is. And if I'm going to save this and refresh, you will see that on each frame, we have this effect printed now because this is remembered. And I don't need this log anymore. It was just to demonstrate to you what happens. Right, so we have now the bottom part animated. It's now 2 versions of me there talking. Let's start the image processing. So I want to get the image data, the image information from every frame within the animate loop. So I'm going to do that by typing here image data is equal to ctx get image data, and I want all of it. So starting at 0, 0, and all the way to the canvas width and canvas height. And let's debug, let's log this image data. And I will also call debugger here so that I don't get the looping effect. It will stop at the first frame and I can investigate this image data there. So let me refresh this. And now it's stopped. You can see video still plays for some reason. And the canvas there is stopped at the first frame. And if I'm going to go here in the console, I can see this image data of the first frame being listed. So it has some properties like the width and height. These are just how my camera operates, the properties of my camera. And then here we get the actual pixel values, which are quite many of them. So this number here is actually 480 times 640 times 4, because for each pixel in this image, I actually get 4 different values. A value for the red component, green component, blue component, and alpha, or the opacity. So this repeats for all the pixels, and it's really a very massive array here that we have to work with. And all these values are not really grouped in any way, and they're just listed one after the other. I would like some structure. I think the code becomes clearer if we use a matrix here instead. A 2D array with 480 rows and 640 columns. So that's what we're going to do next. I'm going to go here and remove this debugging and write matrix, let's call it mat, is equal to get pixel matrix from the image data. Actually, let's debug this as well. So I'm going to write console log mat here and debugger. Now this get pixel matrix function here, let's write it in utils.js, a new file that is going to contain things that are generally useful, not just for this project alone. I'm going to go up here in index.html and include utils.js, save this file, and I'm going to create the new file utils.js here. So how does this function getPixelMatrix look like? Well, let's start implementing it by writing getPixelMatrix and passing the image data here like this. So let's begin by creating the empty matrix first. Mat is equal to a new array, the same number of elements as the height of the image data. And then for each of these rows, we are going to generate new arrays with the same number of elements as the width of the image data. These will be the number of columns. So essentially, a matrix is just an array of arrays. I'm going to return this just to test if what we wrote so far works. I'm going to refresh this, allow, go to the console, and this is it. 480 items. Each of these 480 items is going to have 640 items that eventually will be the pixel values, the red, green, blue, and opacity alpha components of each individual pixel. So I think that this structure is a little bit clearer to understand because we're going to work with XY coordinates of these pixels, and the XY are going to be easily accessible from this matrix directly. You'll see. Now let's add values into the matrix. I'm going to write here a for loop starting at 0 and going all the way to the end of the image data. And I will increase this by 4 because I want it to go pixel-wise. I want to jump over the RGBA components in one iteration. And here I can get the color values like so. I can say p color, like the pixel color, is equal to the red, which is going to be image data of I plus 0, if you will. And then green image data, data I plus 1, so the next one, and then B, the one after that, and A, the one after that. Good. And next, I want to teach you how to get the XY location given this I value and the image data properties, like its width. So let's get the pixel index. We start counting in the top left corner here, and that will be index 0, and then it increases towards the right, and then continues to grow onwards. It doesn't yet know the XY yet, but this is easily accessible. We say p index is equal to I divided by 4. And since we increase here by 4, all the time, it means this number will be divisible, so we don't need to round it or anything like that. So now the question is, how do we get the xy according to these properties? To teach you that, I'm going to use this app where I'm going to pixelate this image. So I'm going to say pixelate, and now p index of 0 is that location. And as I mentioned previously, it's going to increase towards the right. And this image, this pixelated image, it's a very, very small image. It has a width of 32. But the pixel index at this maximum x is just 31 because we started counting at 0. But again, this p index is going to continue to increase according to I alone. And for example, here we get 63 and so on. The question is, what is this value? So given a p index and the width of the image data, can we calculate the x and y? And actually, this is really simple because the difference here, 0, 1, 2, 3, 4, 5, 6, 7, this is just the remainder when we divide p index by the width of the image, 32. So I can write here that the x value of this pixel is going to be p index modulo image data dot width. Now for the height, I would like to get here a value of 0, 1, 2, 3, 4, 5. And that's actually the result when we divide p index again by the width, and we take the floor part, because here, if we divide by that, then we are going to get a floating point number. It's going to be 5 and something. Really, it's the same operation here for x and y. We just take the remainder of the division or the result of the division, the integer part. So these are the x and y values, and here is where we are going to access the matrix and say that the matrix of y, we first give the row, and x is going to be equal to p color. So we store in the matrix the color at y and x. And that's it. I'm going to save this, go back to our application, refresh, allow, and now in the console, this array is going to have values in it. So let's see how these values look like. RGBA, RGBA, and so on. So these first ones correspond to pixels in the top left corner here. So it has a significant amount of green in it. Also some red and blue. These values are never pure when you work with real image data like what I have here. But of course, if I'm going to scroll down this a lot, then probably eventually I'm going to reach part of my shirt. Maybe the bottommost row is going to have easily accessible data for that. So let's open the bottommost row, and here, somewhere in the middle where I expect to see red, maybe here. So very big red, almost no green and blue this time. And all of the opacity, all of the alpha values are 255. So my matrix works. It now representing the image data in a way that it's more easily accessible here. Let me go back to Effect.js and remove this logging from here. We don't need it anymore. So now if I refresh this, everything just moves smoothly and the animation still works here on the canvas as expected. Now, how do we get this image distorted so that it looks like reflected on a round object? We'll get to that, but first I want to remind you about vectors and about converting from Cartesian space to polar coordinates and back. If you don't know what I'm talking about, please watch my video on vectors. I think it's really useful and you'll understand what I mean. To test these vector operations, I'm going to use another canvas. It's going to be a temporary canvas, so I'm going to be sloppy when I implement this next part. But eventually we remove it, so there's no problem. What I do is I want to define a new image data, an empty image data on this new canvas. So let's call this my canvas 2 and my context 2 and so on. So we create image data according to the width of the canvas and the height of the canvas. This doesn't exist yet, so I'm going to go in index.html right here, and I'm going to copy my canvas here with my canvas 2. And I'm going to go here and define a global variable for this canvas context, ctx2. I promise I will remove these things later, so no point to think too much about naming these. So this is going to be the context of this my canvas 2, like this. And here I want that new canvas to also have the same size as the original one. And I think that's it. Now I go back to the effect and I just want to put data in this image data from the original image data coming from the second canvas right here. So let's try to do that. It's going to feel like we're standing still for a while, but I'm going to get somewhere, I promise. I go here and write, let's iterate through this new image data. So it's going to be empty. It just has a width and a height defined by this my canvas 2 width and height, which are all the same, like the video and the other canvas. So going through the data, and again, I'm going to iterate pixel by pixel, so jumping here by 4, and I'm going to get the p index, same as before, and I'm going to get the x, same as before, relative to, I just put here canvas width. All of them are the same, really. And the y in this way. To get the RGBA values, I just have to look in the matrix in this mat and say here RGBA, I'm using object destructuring, is the value of mat at y and x. So first the row and then the column. And let's populate new image data of I is equal to r, new image data of I plus 1 is equal to g, I plus 2 is equal to b, I plus 3 is equal to a. All right, only thing we need to do is set this new image data. We use the ctx method put image data on this ctx2 context, so for a canvas that we aren't even visualizing yet, with new image data, and we started at 0, 0. So all we are doing now is essentially complicated code that goes pixel by pixel, takes from the matrix the values that we have stored there, and puts them on yet another canvas. It really helps to code in this way because in this way, we see that the values in this matrix are actually proper. So I'm going to save this, refresh. You can see already here these two canvases now. So allow, and if I zoom out a bit more, now we have my video, my canvas, and my canvas too. So again, all we did is replicated canvas on my canvas too, with a lot of work. And we're not done yet. The next part is going to be a little bit more theoretical. And in the beginning, again, we are pretty much going to be standing in one spot. So please bear with me. It's going to make sense eventually, I promise. What I'm going to do next is implement the vector utility functions from my video on vectors. And these are going to be the function to convert to polar coordinates given an x and y. I'm going to return here the direction and the magnitude. So vectors can be represented as xy points or the direction and the magnitude. So the direction is the angle and the magnitude is the distance from the 0, 0 point. It's essentially another way of representing the same point. So let me specifically extract this magnitude here and return the length of the hypotenuse between these locations. I don't need to do the difference like you typically do when applying the Pythagorean theorem, because one of the coordinates is always 0, 0. And the direction, we can find this one using the arctangent 2 function of the math library. So do check my other videos if you have questions here. But essentially, if I'm specifying here the y and the x, then this is going to output the angle in radians. And that is the direction of the vector. So let's close this and implement also the reverse operation. So from polar coordinates, we can also go back to Cartesian space or xy space. To do that, we return here the cosine of this angle, of this direction, multiplied by the magnitude. The cosine is just a value between -1 and 1, so we wouldn't be able to represent big values like 640, 480, things like this without scaling by the magnitude. And same goes for the sine on the vertical axis. Two more functions that I want to implement here are the vector addition and subtraction. Really easy ones this time. So given two points or vectors represented in Cartesian space, so the new x is going to be adding the x's of the two vectors. The new y is going to be adding the y's of the two vectors, like this. And we are going to do the same thing for subtract. So it's essentially the same function, but we call it subtract like this, and we put the minus here. Really easy. And if we go back in the effect, I want to test these new functions by converting to polar coordinates each of the pixel values and then converting back to Cartesian coordinates. Essentially, nothing will change, but I'm testing that I'm implementing these functions correctly. So here we have the original xy values that we want to use, and I'm going to try to modify them. So I will write first a conversion to polar coordinates. Let's get the magnitude and the direction from two polar of this x and y, like this. And let's calculate a new x and y. Let's call this new xy is equal to 2xy of the magnitude and direction, like this. Now, there's a problem because doing these operations will cause some things to become floating point values. And in our matrix, we don't have that. The indices in the matrix are integers. So any kind of floating point artifacts need to be fixed by rounding. And I'm going to do that by saying here that the new xy dot x is equal to round of new xy x. And the same thing for the y. Otherwise, we will get an error here where we try to access the matrix element at new xy y and new xy x. But if these are rounded, these are going to be integers, and everything is going to be just fine. So let's see what we have next. I'm going to refresh, allow, and it seems like it's working. As before, there are no... It's not exactly as before. It's slower. I'll show you. I'll superimpose this My Canvas 2 over the original video and make it slightly transparent so that you get what I mean. Let's do it in the elements here. So I'm going to select this. And give it a style of, let's make the position absolute and left of 0 and the opacity 0.5. So here now I actually have two things on top of each other. I have my Canvas 2 and I have the video behind it, but my Canvas 2 is a little bit transparent and I can still see the previous image, kind of like a ghost path there. This slowness is because these functions here are quite demanding. I mean, they are doing trigonometric operations here. This essentially calls the square root at some point. They're not simple operations like addition, subtraction. Even multiplication is more difficult than addition, subtraction, but these go beyond that. So I'm just making the result slower, but the same. And that's about to change now. You see, the idea is to work in this polar space, in the polar coordinates. Let me refresh this and forget about this fancy overlaying where I wanted just to show you how slow this is, and think what we want to do. I essentially want to turn this into this, where pixels around the center are sampled multiple times, giving this impression of a round surface that the image is distributed on. But before we get to that, I'm going to show you this, where the center of this transformation is the top left corner. It's easier that way. So the key to this is to use polar coordinates and change the magnitude somehow before doing the conversion back. I'll show you. Here, I'm going to open up this object a little bit, and I say that the direction can stay the same, but the magnitude, let's replace it with half the magnitude instead and see what happens. You can see here, essentially what has happened is a zooming in on the top left corner here. And what happens is that we are sampling each of these pixels from here twice. So this image here has a poorer resolution. It has duplicated pixels. And it stops at this halfway point because all the magnitudes are halved here. So even the furthest away at the bottom right corner is going to be halved, and that just ends up being here in the middle of this image. Okay, but this is a linear transformation, so zooming is not that interesting. But I should show you what happens if we multiply by 2. And you can probably figure out already, it's an error. It's an error because we are trying to sample here outside of this image all the way to double outside of this image. So that isn't contained in the matrix that we have stored previously. So we need to write some code that prevents us from doing that. If we try to sample from somewhere that doesn't exist, we are just not going to do anything. So I check if the y is within 0 and the length of the matrix, and I check if the x is between 0 and the matrix of the y length as well. And now I'm going to put everything here inside of this if conditional statement and close this curly brace. Refresh, and this is what we get. We put here just half of the image data, and essentially we made this image smaller by now skipping pixels. So we multiply by 2, that means that we are only going to get even rows and even columns from here. And we just learned how image scaling works, both increasing in size and decreasing in size. Now, these are linear transformations and they're not very interesting. I'm going to show you a way to move away from that. And to do that, I first want to calculate what is the largest possible magnitude for these. So essentially, this vector right here is the furthest away from 0, 0. So that's the hypotenuse of the height and the width of this canvas. And I want to record this information somewhere. So I will write here a constant called diagonal equal math so the hypotenuse of canvas width and canvas height, like this. And now I want here to modify this magnitude in a way relative to this diag right here. If I divide the magnitude by the diagonal, I know that this value is going to be between 0 and 1. If I leave it like that, then all I'm going to get here is essentially the top left pixel, pretty much. Let's see if I can trigger this somehow. Yeah. But if I scale this by the value of the diagonal, I essentially simplify this back. So I get back to the magnitude. So much going back and forth, right? But this is where the key part happens. This magnitude divided by the diagonal, I can easily change using some mathematical functions. Like, for example, if I raise this to the second power, then this function is going to be nonlinear. Let me show you. In this Desmos calculator, if I'm going to plot here x, then I'm going to get this function that looks like so. And I'm interested in how it behaves between 0 and 1. So think of x as this part right here, mag divided by diag. It is going to be between 0 and 1, and it is linear like this. But if I'm going to raise this to a power, like x power 2, then this function changes a little bit differently. It also starts at 0 and ends at 1, but it doesn't go linearly like this. Let's see the effect. So save the file, go back here, refresh the page, and this is what happens now. Interesting, isn't it? So if I'm gonna move my hand here, you can see it zooming in somehow. And this is normal. I mean, it's what we are telling it to do. We are telling it that close to this 0 point, close to the top left corner, I want to get more pixels around that location. So it doesn't go far away from that corner so quickly. And this is what you see happening here. My hand starts to have much more pixels in this image than in this image, right? And then gradually this goes back to 1. Now, this image is actually cropped here a little bit. So that's because we are using the hypotenuse here to scale these values. But if we would use, for example, the minimum value, then the result would look something like this, where you could see all the pixels pretty much of the original image. So I'm going to leave it like this to get a better understanding of where the image ends and how it's actually deformed. I think it looks quite clear after doing it. To make the effect relative to the center point, we need an offset. We are going to define here an offset to be the center of the canvas, pretty much. Half the width and half the height. And we're going to subtract this offset here from this xy value when doing the conversion. Let me write this on a new line here. Subtract from x and y the offset, like this. And we need to remember to add it back as well. So here I'm going to add the result of this 2xy converting back function. I'm going to add this to the offset. And now refreshing this will look like that. A little bit funny there. One thing that I want you to notice is that again, the image is cropped. I don't see the top of my hat, for example. And that's because now this diagonal shouldn't be the minimum of these two values anymore. It should be half of that. Because when we moved relative to the center point, we only have half as much in all directions. So if we divide here by 2, we are going to see again the sides of this image appearing there. Now that we got something to work here, I don't think we need this extra canvas anymore. I'll show you. So here we just do all of this processing on top of the existing canvas. So CTX and then canvas, canvas, like this. And here we just do CTX, put image data. So after it's being drawn here, this image that we see here, in the same frame, it's being processed. A new image data is generated using these distortion functions from here and then put back on top of it. It just happens so quickly we don't notice anything. So if I refresh this, now this image right here in the top right corner is the same as my canvas 2. So let me go back in index.html and remove all this ugly code, these global variables from here. And yeah, we're back to working with 2 canvases again. Now, I want to teach you some things about optimizing code and time complexity. So really, the time complexity here is ordo n, if n is the length of that image data array. And it's not going to change no matter how I'm going to optimize this. You can also say that the complexity is ordo n times m if you want to base it on the matrix size instead, like the width and the height. Multiplying those again gives you the size of that array times 4, but that's a constant value. So time complexity is that, but we can make this code faster regardless. I mean, now it's quite slow there. You can visually see how my hand moves really slow in the distorted version compared to the other one. And I think we can do better. So let's see what the problems are here. And I'm going to take things seriously, so hope you can follow along. This offset here, we don't really need to define inside of this for loop. I mean, why define it inside of this for loop? It's always going to be the same, canvas width by height. And actually, this diag as well. So one thing that we can do to optimize this is not repeat these all the time and move them here instead. It will have some improvement. Then the next thing that we could do is here. When we do this polar conversion, we really call a bunch of functions here, which are really nice to read. I mean, everything is clear what this function is doing, calling these other ones, but calling so many functions for each pixel, basically, it's going to be more expensive than calling just the final product from here. So I'm going to do just that. Here, this toPolar is calling many things, and then we have also this subtract here, quite a lot of things happening. What we can do is actually do this offset part of this code right here, say minus offset.x, and here minus offset.y. And here we can just define these magnitude as math.hypot of x and y, and the direction math atan2 of y and x, like this. And this new magnitude here, we can actually have a variable for that as well. So maybe new magnitude is equal to the diagonal times magnitude divided by the diagonal to the second power. And to generate this new xy, I'm going to do it in one line pretty much. I will say new xy is equal to x. Let's start with this round function here. And I'm going to do math cosine of the direction times the new magnitude. So this one that we are calculating there. And we also have to remember to add the offset plus offset.x. And I'm going to do the same thing for y here, but with the sign and the y offset instead. Let's close this. And we don't need this piece of code anymore. I forget here to close this parenthesis for the round. This is what happens when you do too many things in few operations. It starts to become hard to read and definitely very confusing. Comments would be needed, but I want to end this at some point. Maybe it's a good idea to test if everything still works after all these changes. I'm a little bit relieved to see this. So, okay, is it any better? I think it's a little better. I think it's a little faster now. You could do profiling to see how much processing power it's using, but I don't want to overcomplicate things. I want to next show you how we can decrease the memory and probably processing as well. So here, using this matrix, I find it really clear that we have the pixels now scattered in a grid with rows and columns, but we don't really need it. We could just work with the I value directly, like the index directly, and somehow we have to undo the formula from here and generate a new I that we are going to use to get data from this original image data from here. And I'm going to reverse that function like this. I will write new I is equal to new xy times y times image data width. So what we do here, where we calculate the y here, we divide it by the width. So I'm going to multiply by the width. This is going to essentially give me here this rectangle here. So I don't have the remainder yet. I need to add to this the remainder, so new xy dot x. And because all of these were divided by 4 here, I need to multiply back by 4. And now I'm getting where to get the pixel information from without using the matrix at all. I just write here, get it from image data of new I plus 0 in this case. And I'm just going to copy this for all the other ones. 1, 2, and 3. And I don't need this line anymore. And here, actually, this if won't work anymore, but we can write a simpler variant. We can say if new I is less than the image data length, then we should be just fine. So let me put these things inside of this if conditional here and go back to the project, refresh. Okay, something is a little bit different because now we're getting some pixels here, like somehow continuing on the other side there. So not using the matrix has this side effect, but it's not going to bother us. You'll see. So we don't need the matrix anymore. That means that this expensive step from up here can be removed. We don't even need this utility function anymore. And everything still works. Is it faster? I don't know. I think it's faster. I don't see a big lag between my hands moving there. And most importantly, I'm not using a lot of additional memory for that matrix. So time complexity is one thing, memory complexity is important as well. Let's continue with the effect. So I want to keep this result in a circular shape. And that just means that I'm going to keep the values less than, with the new magnitude, less than this diagonal value here. So if new magnitude less than diagonal, and that, then I'm going to update the image data. So that's what I meant, that we don't have to worry about those outside pixels. And let's try to find an image next online that we can put this on top of and make it look nicely. So I'm gonna search for red decoration Christmas. And let's look at Google Images. I'm going to look at those that are free to use. This looks quite nice. So let's get this image. Crosswalks. Okay. Motorcycles. Where are the motorcycles? I don't see any motorcycle. So I moved it here in the project folder and I renamed it background.jpg. And we are going to set it behind our canvas, essentially. So I'm going to go to index.html and I'm going to wrap this canvas in a div. I will call it canvas container. Let's indent this and close the div. And now inside of style CSS, I'm going to put this canvas container to have a background image with this given URL. So background.jpg. And the size of this image is 360 pixels times 540 pixels. I checked earlier. And we don't want to have the background color of the canvas blue anymore, because then we wouldn't see this background image. And actually, let me hide this video. We don't need it anymore either. So display none. And there it is, something. I zoomed in a little bit. And now my job is to find some transformation for this canvas so that this looks like it's on top of that globe there. So let me try this here by playing with the CSS. I'm gonna say width maybe 200 pixels. This is a bit small, but let's try to position otherwise as well. So margin top 300 pixels, maybe less, something like this. And let's increase this now, maybe 300 pixels. Okay, this looks good, but the margin top has to be even higher, something like this. And let's add the margin left as well, minus 10 pixels. Something like this. I think it looks as good as it can get. So I'm going to copy this in the canvas element here. Save, refresh, and now the canvas comes exactly there. Now, the trick to get this to look like it's on the red globe is to change the color of the pixels here. I'm going to focus on the red channel only. So I go back here to Effect.js, and actually here I don't want the green and blue information at all. I just want to focus on the red information. Something like this. Yeah, but actually these are not needed because this image data is already has zeros for those values, so waste of computation. So we can remove that and the result is still the same. And I would like somehow this edges here to be a little bit more fuzzy. So now it looks like it's some kind of sticker on top of this image and it doesn't look good. Let's try to fix that by modifying the opacity here for the last one according to the relationship between the new magnitude and this diagonal value. So I'm going to put here new mag divided by diagonal, and this is going to be a value between 0 and 1, but it should be between 0 and 255. So I scale it like that. And it should be an integer value. So let's say math.round here as well, like this. And now it's exactly the opposite of what I wanted. The middle of the image is transparent. I want opposite of that. So 1 minus this value there, refresh. And now these sides here fit much more nicely. Let me show you what I did by removing this background. So basically here you have fully visible pixels and their transparency goes less and less as you approach this endpoint. You could play with this more if you want, like if you want to have more visible pixels here, maybe scale this, like maybe raise it to the second power. You can play with the Desmos again and see what I'm doing. But essentially, it's now having more pixels close to 1 in opacity. I mean, 255 in opacity. And then only closer to the end, you really get back to 0. So this looks a little bit nicer because I'm not fading so rapidly from the center point. Yeah, I really like this result now. And of course you can see the structure of this background globe better as well. But I think that we can do much better with this optimization, so let's give it one more shot. You see, this transparency here that we are calculating doesn't really need to be applied on each frame of the animation. Actually, none of these things have to be. We could move all of these things up here as attributes when we initialize the effect. So this wouldn't be executed every time we animate. We just store these as attributes like this. This should work, but the CTX needs to be this as well. So this new image data offset and diag, I want to add them here to the destructuring assignment. So diag new image data and the offset. All of these are now accessible here as such as before, but they are not initialized on each frame. And actually here, this information, this alpha property, doesn't need to be set on each frame. This is always going to have the same kind of opacity structure there. So if I go really crazy, I could move this instantiation of the alpha values up here as well. Let's try to do it. So it's going to be really ugly and messy, but it's my video. I do what I want. So I'm going to copy this up here. And I need to copy this. So going through the new image data, I need this pixel index. Yes, I need the X and Y, the magnitude, the new magnitude. I need it. Diag here is this diag now. New XY uses this offset there. I'm not sure if I need this one. What do I need here? I need new magnitude and diag. So new magnitude, I need it. But after that, I don't need this parts anymore. I need new Y. Okay, and image data here doesn't even exist, but I could use this new image data instead. So yeah, I can use it because I don't have to set the R value. I just want to set the alpha value here. So the alpha value comes from new mag and this diagonal with this crazy formula here. And this diag here. I think this should work. So now after setting this alpha value with very similar code as before, I'm forgetting this right here. Yeah. Then I don't need to do it here. And this is some calculation again. It's some squaring here and different things. So this is a speed up again. Let's save, refresh, and hope it works. Okay, amazing. It seems to work. So the fade effect is still there happening. Let me put back the background. And the speed is, I think this is pretty much as fast as it can get. If you can do it better, let me know. But I'm not going to bother with it anymore. I do want to tell you that I lied to you. This formula here, it's not really proper. I mean, I showed you how to somehow use a non-linear way to calculate the magnitude, but this is not the correct way to do it if you think about physics and how these kind of um, convex mirrors work. So I don't teach you that. I encourage you to figure it out by yourself. Thanks for watching. Were you able to follow along? Even the optimization part? Let me know in the comments what level you think you are, and remember that the number goes quite high nowadays. Also, check out the version on my website. It's a bit more advanced and it allows you to take a picture as well so you can share it on social media. Merry Christmas and see you guys.